Now today we are discussing about other types of protective relays. So the contents of the protective relays are in this session are like this, see in the caption. First one is induction type directional power relay, that is directional. Second one is induction type directional overcurrent relay. Third one is distance or impedance relay. Fourth one is differential relay, current differential relay. Fifth one is percentage or biased beam relay. Fourth one is types of protection, and last one is objective type questions. So coming to first one, that is induction type power relay, that is directional power relay. So these relays are operates whenever a power flows in a particular direction. So these relays are operates whenever power flows in a particular direction. So that is the torque is depend upon the both voltage as well as current of the circuit to be protected. Hence this is type of a wattmeter. This is one type of a wattmeter, like that. So in this relay the direction of torque depends upon the direction of the current or power to be flow in the circuit. So first one is induction type directional power relay. So as seen in the figure, the construction details are like this, as seen in the figure. So it has a two electromagnets. So first one is here the voltage is applied to this upper magnet at the central limb. So here it is protected, provided here the voltage is applied through potential transformer, that is PT is connected here. From the PT the winding is connected. So the winding is placed upon the central limb of the upper electromagnet. So next one is, second one is winding of the upper winding. Third one is, this is goes to the trip circuit from fixed contacts. So here is the moving contacts, the bar like is, this is the moving contact attached to the spindle of the disc. So this is the spindle and here it is the disc, where the disc is rotated between the upper and lower electromagnet, right. So lower electromagnet is provided another winding. This winding is called as current coil. So this current coil is connected to the secondary terminals of the CT. So 5 is, here it is the 5 is CT, current transformer. Here it is connected to the current coil is connected to the potential current transformer. So here also number of tappings are provided here. This is the tapping bridge, plug bridge. So number of tappings are provided. So these number of tappings are giving us different current settings. Fourth one is lower electromagnet. So in this voltage as well as current both are provided. Here the voltage is provided here of the circuit to be protected. Here the current is provided through the current transformer, so that both voltage and currents are provided. And here is a disc. The disc is rotated depend upon the interaction of the fluxes induced in the disc. This is pi 1. This pi 1 is due to voltage of this electromagnet, and this pi 2 is current of this electromagnet. So these two fluxes are acted upon the disc, and hence the disc is rotated against the spring, that is the restraining force provided here under of the disc. The spring is provided under of the disc. So the construction is like this. So working under normal conditions, voltage and currents are flows in such a direction that the fluxes developed in the disc are in a direction, the torque, that is the driving torque, as well as the restraining torque, both are in the same direction. So therefore the disc cannot rotate it under normal conditions. So whenever a short circuit occurs on the system, in this way short circuit occurs, what happens? Current increases and voltage, that means current can flow in either direction. It is flows in a reverse as well as forward direction. So here in this particular case, we will see the current flows in a reverse direction. So therefore the current flows in a reverse direction, the power also flows in a reverse direction. In this way the torque applied on the disc, that is the driving torque, is reversed against the restraining torque. Therefore the disc is start to rotate, and it rotates as well as its moving contact also rotates and touches the fixed contacts of the trip circuit. Then the trip circuit is closed, the trip circuit is engaged the or energizes the circuit breaker, and then the circuit breaker which isolates the faulty section from the healthy section. Like this the directional power relay works. So coming to next one, induction type directional overcurrent relay. So next one is induction type directional overcurrent relay. In this relay, the directional, that means power relay, as well as overcurrent element, these two are incorporated. In the previous section we are discussing overcurrent relay, in this session we are discussing power relay. So in these two relays are incorporated in this relay, that is the two relays or two elements are placed in a common case. So why this relay comes into picture? Because under short circuit conditions in the power relay the voltage decreases. So the voltage decreases, what happens? The flux decreases. Then flux decreases, the driving torque also decreases. So the driving torque decreases, what happens? The disc cannot rotate. So the disc is in, the relay is inoperative. That means the relay cannot operate. So in this situation, these power relays are not suitable for short circuit, because you see the vector diagrams of the directional power relays like this. So here is the voltage applied to the circuit to be protected through potential transformer, and here it is the flux pi 1. This flux pi 1 is derived or proportional to the voltage, and it is lagging behind the voltage exactly 90 degrees. So this is the exactly 90 degrees, and pi 2 is derived from the current to be protected, and it is in phase with the current. So this is the phi 2 in phase with the current. So current vector also in same direction, same way, right? So and this current or flux pi 2 is lagging behind the applied voltage some angle called theta. This theta is known as power factor, and the angle between pi 1 and pi 2 is given as alpha. So in that way the torque is T, the operating torque T is proportional to pi 1, pi 2, and angle between them, that is sine of angle between pi 1 and pi 2, sine alpha. Then pi 1 is proportional to voltage, that means this pi 1 is derived from voltage and pi 2 is derived from vectors. Therefore pi 1 is proportional to V, pi 2 is proportional to I, and alpha is in terms of theta, that is this alpha is we can written as 90 minus theta. So alpha equal to 90 minus theta, and replacing pi 1, pi 2 and alpha, T is proportional to Vi sin 90 minus theta, then sin 90 minus theta equal to cos theta. So Vi cos theta. So Vi cos theta is voltage, current and angle between them is nothing but power in the circuit. That means the operating torque is proportional to the powering circuit. So in this way the directional power relay, when short circuit comes, what happens? The voltage decreases. So voltage decreases, what happens? Pi 1 decreases. So what happens? Pi 1 decreases, total operating torque decreases. So operating torque decreases means the relay is not suitable for operation of short circuits. So in this way, these power relays, directional power relays, are inoperative at short circuit times. So in this way, there is another relay which comes into picture, that is both incorporated, that is power and as well as directional as well as overcurrent elements. This relay is known as induction type directional overcurrent relay. So constructionally the relay is like this, as shown in the figure. This is a induction type directional overcurrent relay. So here it is the overcurrent element, this is the one is the overcurrent element. So overcurrent element consists of upper magnet as well as lower magnet as well as trip circuit contacts. Number 2 is the trip circuit contacts and disc or spindle, and third is the directional element. Directional element means power relay. It is similar to directional power relay. It has also an upper magnet and also lower magnet. So coming to this magnet, this is directional relay. The directional relay or power relay, it consists of two electromagnets. In between two electromagnets there is a disc provided here, aluminum disc, and this aluminum disc is over a spindle, and this spindle carries moving contacts. This spindle carries a moving contact here, and there is a contacts also here. So first one, winding. So upper electromagnet, that is the directional power relay. Upper electromagnet consists of a winding. This is called potential coil. This is called potential coil, wound on the central limb, and this is connected to the potential transformer of the circuit, that is the voltage to be protected. Voltage to be protected is connected here, and lower electromagnet is called current coil, and this current coil is connected like this. This current coil is connected to the upper electromagnet of the overcurrent element or non-directional element central limb, this one, and this has many number of tappings, and these tappings are connected to the plug setting bridge. This is the plug setting bridge, and from the plug setting bridge it is coming to here, and it is this 5, number 5 is connected to the current transformer, that is CT of the line to be protected, and here it is the trip circuit contacts. So here also lower electromagnet is connected a winding, and this winding is connected to the contacts, that is the fixed contacts of the power relay, directional power relay, like this. So this is one winding, one terminal, and this is another terminal connected here on the central limb, and it carries a aluminum disc. This aluminum disc is provided on the provided with the spindle, and the spindle carries a moving contact, right. So this is the constructionally a directional overcurrent relay. Coming to its working, under normal working conditions, the current flow in the circuit or power flow in the circuit is normal direction. So therefore the directional power relay cannot operate, because the overcurrent element operates when the power relay operates. That means first power relay operates, then only the overcurrent relay activates. So here power relay cannot operate, because the direction, the current direction as well as the power direction under normal circuit, under normal working condition is normal. So in this way the relay cannot operate. But whenever a short circuit occurs, then the direction of the current or power flows in reverse direction. So in the reverse direction, the torque developed on the disc of the directional power relay also reversed. So in this way the disc rotates against the restraining force, that is the restraining force is provided by the spring control. So the driving torque is large enough, so it overcomes the restraining torque, and the disc starts to rotate and touches the fixed contacts. So where the fixed contacts are again connected to the secondary circuit of the overcurrent element, that is the upper electromagnets of the overcurrent element. So in this way the secondary circuit of the overcurrent element closes, then the overcurrent element starts, its operation starts, then the disc of the overcurrent element starts to rotate. In this way the moving contacts also rotates, and the moving contacts touches the fixed contacts, then the trip circuit is closes, then trip circuit is closes, the circuit breaker is activated, then the faulty section is disconnected from the healthy section. Because here the relay is provided, it is provided with such that the voltage as well as the power factor effects are minimized. That means in the previous case the voltage effect is much more because of the operation of the power relay under short circuit conditions. Here these effects are somewhat minimized, that is why these relays can be used as protective relays for short circuits. So in this way how the directional power relay, directional overcurrent relay works, because how the tripping occurs in these relays. So for this purpose there is three conditions should be fulfilled. That three conditions are like this. So final tripping occurs when direction of current or power is in reverse direction. Second, current exceeds pickup value in the reverse direction. This reverse current exists longer than its time setting. So in this way overcurrent relays are both current setting as well as time setting. So the relay operates whenever the pickup value exceeds, whenever the time exceeds, then only the relay operates. So like this the overcurrent directional overcurrent relay works, and the advantage of this relays are like this. That means applications of the directional power relays are directional overcurrent relays are like this. These relays are employed when graded time overload protection is applied to ring mains and interconnected networks, since fault current can flow in either direction. So there these relays are used. So these are the applications of the directional overcurrent relays. Next, coming to third type of relays, that is impedance or distance relays. So these relays are already explained in the previous class. How these relays are operated? These relays are operated of the ratio, that is the voltage to current ratio. These relays are operated when voltage to current ratios are falls below a predetermined value, that is nothing but impedance or distance. So predetermined value is some impedance, but these relays are operated whenever the impedance or ratio of V by I falls below a predetermined value, then these relays are operated. So a basic relay is shown in figure, as shown in the figure. You see in the figure the basic type of the operation of the relay is like this. Here is, this is the transmission line, this is the generator feeding the transmission line like this. So this is the transmission line. So this transmission line, the protected area is or section is A, B. So in this section is only that line is protected. The section is AB section only protected. Here this is the relay. 3 is the impedance relay. We call it as the impedance relay. Here the CT is connected in series with the transmission line to be protected, and the PT is connected across the line to be protected through potential transformer. So in this way the relay is connected. The relay operates like this. The working of the relay is like this. In these relays the torques, that is torque due to voltage and torque due to current, both are compared, and these both are in the opposite direction. So these both are compared, then the ratio is taking up, that is V by I. This means which torque or which pull is greater than that, then only the relay works. Suppose, see in the figure, there is a fault. F1 is fault between section A and B, and F2 is fault beyond the section AB. So consider first fault at section within the AB. So this here. So due to this, what happens here, the short circuit occurs at F1. So in this way, what happens, the voltage of the circuit decreases or falls below, whereas current increases. So in this way, the torque due to voltage is decreased, whereas the torque due to current is increased, and these two torques are in the opposite direction. So in the same way, the ratio of V by I also less. So in this way, it is a predetermined value, that is the ratio V by I under fault conditions is less than the predetermined value. Then the relay, that is the impedance relay, operates and it disconnects the faulty section along with circuit breaker. So suppose a fault occurs at point F2, see in the figure, that is the fault occurs at point F2. So here the short circuit, here also short circuit occurs, but here the voltage as well as current are such that the ratio is greater than the predetermined value. That means that impedance is greater than the predetermined value, and hence the relay cannot operate, because the relay operates only when the it is less than the predetermined value, that is the ratio less than the predetermined value, only it operates. So like this the relay is operated. Next, coming to its types of distance or impedance relays. There are two types of distance or impedance relays. Those are, first one is types of distance relays. First one is definite time distance relay or impedance relay. So which operates instantaneously for faults up to predetermined distance from the relay. So these relays are operated instantaneously. So second category of relays are like this, time distance relay. So in the time distance relay, in which operation is proportional to the distance of fault from the relay point. A fault nearer to the relay will operate it earlier than a fault farther away from the relay. So this is the second category of the distance or impedance relay. So you see first type of relay. The first type of relay is like this. The first one is construction of the distance time, definite distance time impedance relay. So like this, the distance impedance relay is like this. So it is provided 1 and 2. 1 and 2 are the armatures. 1 and 2 are the armatures of the electromagnets provided on the common platform. This is the common platform or beam. So these are the armatures, and this beam is attached to a fixed point, that is the fixed contacts, provided with the fixed contact, and these two contacts, this is also fixed contact, but this is the moving contact, this is the fixed contact. This fixed contact is connected to the trip circuit, that is 3 is the trip circuit, and fourth one is the magnet, current excited electromagnet. Fourth one is the current excited electromagnet. Fifth one is the voltage excited electromagnet, and here it is a pivot. This is the pivoted beam provided. This is the beam, pivoted beam hinged to the inject to F. So constructionally the relay is like this. So coming to its operation, under normal working conditions, here under normal working conditions, the pull of the voltage, that is this magnet, the pull of the voltage of this magnet is greater than the pull of the voltage of current magnet. This is the current magnet, this is the voltage magnet. So the pull of the voltage magnet is greater than the pull of the current magnet. So in this way the moving contact is away from the fixed contacts. But whenever a fault conditions occurs, what happens? Short circuit conditions. That means the voltage decreases, current increases. In this way the pull of the voltage decreases, the pull of the current increases. In this way the beam is tilted in this way, in the current direction. So in this way the moving contacts also moves and touches the fixed two contacts, and it goes to the, and it closes the trip circuit. Then the trip circuit energizes the circuit breaker, and this circuit breaker disconnects the faulty section. How these two pulls are related is like this. The two pulls are related like this. The pull is proportional to voltage. The pull of the voltage is proportional to V square, and it is provided with constant K1. This is related to the armature one. Similarly, the pull of the current magnet is proportional to I square, and it is related with K2. This is the constant of the armature. So the relay operates when K1 V square, that is the pull is less than K2 I2 square. That means V2 square by I2 square less than K2 by K1, and V by I is less than K2 by K1, that is Z is less than K2 by K1. So here is K2 by K1 is the predetermined value. So thus under fault conditions the impedance is less than the predetermined value. Then the relay operates, and it operates the circuit breaker which disconnects the faulty section. Like this the relay works. The other type of relay is distance time relay, time distance relay, and constructionally the distance time relay is like this as shown in the figure. So it is essentially a overcurrent relay. It is essentially a overcurrent relay. So this is the exactly overcurrent relay elements, right? So first one is restraining voltage magnet. This is called as restraining voltage magnet. Here one, this means the winding of one is excited from the voltage of the circuit to be protected through the PT, that means potential transformer. Here the voltage is applied to this winding is through potential transformer, and that voltage is a protected voltage of the circuit, and it is attached, here it is an armature. This armature is attached to the spindle, and the spindle also carries the moving contact. Here it is the moving contact, here it is the fixed contact, and fourth one goes to the trip circuit. Again the spindle is also connected to the number 3. Here the number 3 is called spiral spring. This is known as spiral spring. This spiral spring is coupled to the spindle of the overcurrent element. This is the overcurrent element. Sixth one is the overcurrent element. So the spindle of the overcurrent element coupled to the spiral spring. 2 is the restraining voltage magnet. Fifth one is the current. That is the, here the central limb is a winding. This winding is fed with the current of the circuit to be protected through the CT, current transformer, right? So here it is the current is fed through this, here it is voltage is fed this. So in this relay also voltage and currents both are compared. So coming to its operation, the relay is operate like this. Under normal working conditions, what happens? Here the voltage of this magnet is sufficient to hold this armature in this position. So in this way the two fixed contact, the moving contact also away from the fixed contact. But whenever a fault occurs on the system, what happens? The current of the circuit comes into picture, and this current, due to its fluxes, interacts on the aluminum disc, and this disc starts to rotate. As well as this disc starts to rotate. In the similar way, the spiral spring also wounded upon this way. So this spiral spring also wounded, but this disc is proceeded to rotate, as well as this spiral spring also rotated, and this spiral spring rotation, that is the tension of the spiral spring, is sufficient to pull the armature against the magnetizing force of this magnet. That is, the spiral spring is rotated and it pull in this way this armature against the magnetism of this relay, this voltage coil. So in this way the total spindle is moving in this direction. So what happens? This moving contact is touch the fixed contacts. Where this fixed contact touches, then the trip circuit is closed. Then the trip circuit energizes the circuit breaker, and the circuit breaker disconnects the faulty section from the healthy section. Like this the relay works. Here the operating time is like this, of this relay is like this, as seen in the figure. T is operating time proportional to V by I, and is proportional to Z, and Z is proportional to distance. So like this, operating time is proportional to distance of the relay from the fault point. So this is the other type of, that is the second type of distance relays. Next, coming to other types of relays, that is differential relays. So these differential relays are comes into picture because in the previous relays, that is overcurrent relays, power relays, those are inoperative at the time of short circuit, because they cannot make correct distinction between major fault conditions and minor fault conditions. So in this way the differential relay comes into picture.
Hello.
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 How the directional relay will operate? Can you explain?
Directional relay.
Yes, please.
Directional relay means power relay. Here power relay is proportional to, operation is proportional to direction of power. Power relay operating torque is proportional to power. So at the time of short circuit, what happens? The current reverses. That means the power also reverses, that is the direction of the power also reverses. In this way the torque applied on the disc is in the reverse direction. That is, in the previous, under normal working conditions, the direction of operating torque is in the forward, suppose say forward direction, but under short circuit conditions the direction of the disc is in the reverse direction. So in this way the disc is rotated in the reverse direction, and also moving contacts also rotated in the same direction and touches the fixed contacts. Then the trip circuit isolates the faulty section along with circuit breaker. Like that the directional or power relay works. So coming to differential relays. So the differential relay works like this. Is one that operates when the vector difference of two or more electrical quantities exceeds a predetermined value. So here two values compared, that means either currents or voltages to be compared. According to this comparison the relay operates. So these are the working of the differential relay. Next, types of differential. Next, coming to how the differential relay works. So as seen in the figure, the differential relay is like this. So here it is the one is the operating coil of the overcurrent relay. So one is the operating coil of the overcurrent relay. That means the differential relay is nothing but a overcurrent relay, but its connection is some way different. So one is the operating coil of the overcurrent relay, and two is the protected winding, that is the alternator winding. This is the alternator winding to be protected here, and here it is CT, here it is CT. 3 and 4 are CTs connected in series with the winding to be protected, and the CT's ratio is transformation ratio is 200:1. So both are similar, 200:1, and this the restraining coil, the operating coil is connected in between the two CTs of their secondary, that is it is connected across the secondaries of the CTs. The winding is connected across secondaries of the CT. So here the difference, whenever in this winding, that is the operating coil carries differential current, then the relay works. So first see, there is two, we will see the working of this relay.
Hello?
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 Can you give some applications where directional overcurrent relay will be used?
Directional overcurrent relays.
Yeah.
So the directional overcurrent relays are used for short circuits of the transmission lines, transformers, feeders, and alternator windings. So directly directional overcurrent relay is not recommended for the protection of these relays, because it is incorporated some connection methods. So in that way these relays are useful, but these relays are used for protection of alternator windings or transformer windings or feeders, right? So working of these relays are like this. Here we will consider two types of operation. First one is the operation of the first one is like this. So here how the relay operate is like this under normal working conditions. Under normal working conditions, suppose the relay winding, the alternator winding carries a current of suppose 1000 amperes. This alternator winding carries a current of 1000 amperes. Then the current in the CTs is I2, that is I2 is equal to here I2 is equal to transformation ratio into I1, that is N2 by N1 into I1. Here N2 is 1, N1 is 200, and I1 is the current of the alternator winding itself is the primary current of the CT, that is 1000. So here the secondary current of the CT is 5 amperes. Secondary current of the CT is 5 amperes. So in this way the 5 amperes flows in the two relays, that is two CTs 3 and 4. So the 5 amperes flows like this in this relay, and here also the 5 amperes flows in this way. That means here the direction, it is here the direction. So no current is flows in the operating coil of the relay under normal working conditions. Hence this relay cannot operate under normal working conditions. Whenever a fault occurs on the system, here we consider two types of faults. So first fault is like this. Suppose the fault occurs on the alternator winding like this. As shown in the figure. So here the alternator winding, here the earth fault comes. So in this way, here the earth fault point is feeded in this way 2000 amperes. In this way the current flows outside this fault point 500 amperes. So this 500 amperes flows through this CT, and the secondary of this CT is gives us 2.5 amperes. Similarly, the 2000 amperes flows in this CT, that means current transformers, and the secondary current is 10 amperes. So the 10 amperes is coming like this in this, and 2.5 amperes coming like this. So the difference of the 10 minus 2.5, 7.5 amperes flows in the operating coil of the overcurrent elements. So in this way, whenever current flows in the operating coil of the relay, then the relay operates the trip circuit, then the trip circuit isolates the faulty section through CB. So this is one type of fault. Next, other type of fault is like this. Suppose the earth, that is the earth point, the fault point of earth is feeding both ways, that means like this, you see in the picture. So this is the earth fault occurs on the winding. This fault is feed with in this way 1000 amperes, in this way 2000 amperes. So this 1000 amperes flows in this CT, and the CT primary current is 1000 amperes, secondary current is 5 amperes. Similarly, 2000 amperes flows in this winding, and also in this CT the primary current is 2000 amperes, and the secondary current is 10 amperes. Then the 10 amperes comes like this, and 5 ampere also comes like this. So total 15 amperes flows through the relay. Hello? Hello?
Where your balanced beam relay will be used?
Balanced beam, that is biased balanced beam, we call it as, that is coming to the next, that means in the next topic, biased beam relay. We will explain after that. You ask the question. The biased beam relay will after this relay, this differential relay, that is called differential relay. We called as differential relay. Differential relay is called as percentage differential relay or biased beam relay. Now we are discussing the only differential relay. In the next coming, we will discussing about the percentage differential relay or biased beam relay. It is coming after this relay, after operation of this relay. So in this way, here the fault current, that is 5 amperes coming like this, 10 amperes coming like this. So total 15 amperes flows through the operating coil of the overcurrent element. So whenever the current flows through this relay, the relay operates and the trip circuit closes, the trip circuit activates CB disconnects the faulty section. Like this the relays are works. So these are the differential relays. So some of the objective type questions are there. We will go to the objective type questions. So any doubts we will ask now. So object type questions. So first we will look upon the what we are discussed. First we are discussing about the power relay, that is directional power relay, induction type directional power relay. Next one is induction type directional overcurrent relay, that is power relay as well as overcurrent relay, both are incorporated in this relay. And third one is distance or impedance relays. So these relays are also explained, time distance as well as definite time distance relays. And fourth one is differential relays. How these differential relays are also explained with taking two types of faults. So in the next coming section we will discussing about the other relays, that is percentage differential relay or biased beam relays. So we will discuss these relays in the next coming section.